Very similar, it looks like, to other languages. Not easy. And what the precedence here is, if I do not false and false, do I get false? Okay, so it just applies that first one. So it looks like they have the same precedence. So if I wanted to negate the entire thing, I'd have to put the parens around it. Cool. Equality looks to be pretty similar as well. So it's just double equal sign. And not equals is a little different, so that one's going to take a little getting used to. Slash rather than something like that, which is what I'm generally used to. If I'm equal to 4, we'd expect that to be true, obviously. Cool. And then we can string compare as well, it looks like. Cool. Alright, so next it's talking about using these operators, either like the plus or the equivalent or equality checks, with two differing types, it looks like. So if we try to do like 5 plus llama, oops, it'd help if I get the right error. Okay, so it's saying no instance of num array of character arising from the use of plus expression 5 plus llama. Cool. So what that is just saying, I guess, is that there is no known way of using this operator with these two types of values. The other option, or the other example I was giving, was true is equivalent to 5, which again, we have a similar looking error. So it gives us like, it looks like the type of the first. Interesting, I don't know why it's always numpool. Because I'm assuming if we do it this as well, we'll do num, okay, I don't know why it does in that order, but cool. So saying, we may not have known it, but we've been using functions now all along. For instance, star is a function that takes two numbers and multiplies them. As you've seen, we call it by sandwiching it in between them. This is what we call an infix function. Most functions that aren't used with numbers are prefix functions. Let's take a look at that. So functions are usually prefixed, so from now on... Actually, hold on, let me try something real quick. So if we want to do the normally infix function as a prefix, we just have to put parens around it, and then we can pass the two values. So these two are equivalent, right? And then that's not equivalent because we now switch the order, which would be 4 minus 5 instead. Functions are usually prefixed, so from now on we won't explicitly state a function is of the prefix form. We'll just assume it. In most imperative language functions are called by writing function name and writing its parameters in parentheses, usually separated by commas. In Haskell, functions are called by writing the function name, a space, and then the parameters, separated by spaces. For a start, let's try calling one of the most boring functions in Haskell. Suck 8. Gives us 9. So this function takes anything that has a defined successor and returns that successor. Cool. As you can see, we just separate the function name from the parameter with a space. Calling a function with several parameters is also simple. The functions min and max take two things that can be put in order, like numbers. Min returns the one that's lesser, max returns the one that's greater. Cool, that makes sense. So if we just want to do min between 10 and 100, we should get 10. And if we do the same, we should get 100 this time for max. And it looks like it also works for floating point numbers. Oops, not min twice. Brain fart there. Okay, yeah, so it's 0.99. Sweet. Alright, function application. Calling a function by putting a space after it and then typing out its parameters has the highest precedence of them all. What that means for us is that these two statements are equivalent. It looks like they have these two here. Clear some space, so we're going to call the successor of 9. We're going to add that to the max of 5 and 4, and then we're going to add 1 afterwards. So that's going to give us 16. And that is the same as if we were to write it this way, which is kind of like the implied version of all this, right? Oops. But since the function application is the highest precedence, it will apply this one and then this one before evaluating the result of that plus the result of that plus 1. So saying if we, obviously, however, if we want to get the successor of the product of the numbers 9 and 10, we couldn't write successor 9 times 10, because that wouldn't get the successor of 9, because that would get the successor of 9, which would then be multiplied by 10.
Stop it now, I mean it.
Right, okay, so that is the same as this, right? But given what we just did above, it might be assumed that we'd want this instead, right? Which obviously gives us 91. So I wonder if that, nope, okay. Right, so we just have to do it like that if we wanted to force the infix operator before that. Just because the function application, I guess, works a little differently in that case. Makes sense. Okay, if a function takes 2 parameters, we can also call it as an infix function by surrounding it with backticks. For instance, the div function takes 2 integers and does integral division between them. So if we were to do div 92 and 10, we'd get 9. Cool. But when we call it like that, there may be some confusion as to which number is doing the division, which one is being divided. So we can call it as an infix function by doing 92 div 10, and suddenly it's much clearer. So that is the same as this. Cool. And obviously it's different than just using the division, because that will keep the floating point. It's not integer division in that case. So honestly, I don't see how it is too difficult to read this, but maybe in larger bits of code, in larger sequences, it would be easier to use div as an infix just to have it read a little bit more naturally, or a little bit more similar to kind of like the built-in slash that we use a lot of times, huh? So it says lots of people who come from imperative languages tend to stick to the notion that parentheses should denote function application. For example, in C, you use parentheses to call a function like foo, parentheses, bar, parentheses, 1, or baz, parentheses, and then 3 comma, haha. Like we said, spaces are used for function application in Haskell, so those functions in Haskell would be foo, bar 1, baz 3, haha, all with just spaces between. So if you see something like bar, open paren, bar 3, close paren, it doesn't mean that bar is being called with bar and 3 as parameters. It means that we first call the function bar with 3 as the parameter to get some number, and then we pass a bar again, or we call bar again with that number. C, that would be something like bar 3. So this isn't a legal thing here, or legal syntax. So it's kind of just pseudocode right here. Bar 3. So on the left, that's roughly what we'd write in Haskell to apply some function called bar with the value 3, and then use the result of that and apply that to another invocation of bar. But on the right is kind of how we'd write it in JavaScript, C, things like that. Alright, so now it has me doing Babby's first functions. Cool. In the previous section, we got a basic feel for calling functions. Now let's try making our own. Open up your favorite text editor and punch in this function. It takes a number and multiplies it by 2. Alright, so we will just create this, and it looks like they are calling it baby.hs, so we will call it the same. Maybe. I have a new keyboard, and I am not as accurate with it as I'd like to be yet. Alright, cool. So we have our file, and it is telling us to create a function that takes a number and multiplies it by 2. So they were calling it double me x, and x plus x. So we will save that. Functions are defined in a similar way that they are called. The function name is followed by a parameter separated by spaces, but when defining function, there's an equal sign, and after that, we define what the function does. Save this as baby.hs or something. Now navigate to where it's saved and run at GHCI from there. Once inside, do :L baby. So this is just going to load up that script. Cool. Compiling main baby.hs interpreted. Okay, one module loaded. We are good. Sweet. That means that we can now call the function. So we called it double me, and let's call that with 9. Cool. We got 18. It also looks like it can use floating point number or fractional numbers. So 16.6 on the double of 8.3. Looking good. Because the plus operator works on integers as well as floating point numbers, anything that can be considered a number really, our function also works with on any number. Let's make a function that takes two numbers and multiplies each by 2 and then adds them together. Okay? So this one's called double us, and it's taking x and y. So there's our spaces again for defining the function, no commas, no parens, anything like that. And then we are going to have x times 2 plus y times 2. Cool. Let's load that up again. And now we have double us. And if we pass it 4 and 9, we get 26. And if we have 2.3 and 34.2 as their example shows, we should get 73. Awesome. But I don't think it would work if, well, actually it would probably work if we did like this, right? Because it would just convert this to a floating point number, I believe, under the scenes. So yeah. I wonder, I don't think it does any sort of like overloading, right? So if I do like hi, yeah, okay, so it does look for a number here. It does look specific enough for that. Need to take a drink of some coffee here, 1 second. The last example looks like it's going to use both double us and double me, so let's take a look at that. So double us first takes this, then it takes 28, 88 plus double me of 123, 478. Let's see what that looks like here. So is it that it's taking the double us first and then adding the double me? It looks like it is. If we wanted to take 88 plus the double me before double us, that would give us a different value. And also, let's see if we just did this. Double us, double me. Does that work? Okay, so can't figure that one out. So I would need to make sure that this gets invoked first. Okay, so I'm not really sure again what a lot of this means, so I will kind of learn how to read these. My understanding is that this is a type signature. I have some understanding of Haskell. It's been a while though, so I'm just gonna play dumb for now. And not that that's far off from the truth, but I'm gonna try my best to not like jump ahead and try and guess what some of these things mean right this second. Alright, so it's like saying, as expected, you can call your own functions from other functions that you made. With that in mind, we could refine double us. So instead of doing it like this, we could use our double me function. And we could do this. Double me x plus double me y. And that should give us the same value. So now if we load this up and run our same thing here, we should still get our 478. Excellent. I think that's a pretty big distinction, right? So my understanding is with a lot of functional programming, you really want to make very, very small units of work, which you'd be wrapping in functions, and then you want to heavily reuse those functions in places where it makes sense. The reason being is for testing purposes and for refactoring and for just code maintenance in general. In this case, obviously, doing like x times 2 and y times 2 isn't the end of the world. It's pretty set in stone that is what it's going to do, but obviously if for some reason double me came along and changed the semantics at some point, or the concept of doubling changed, it would be good to have it in one place that we can change it instead of a bunch of places. But I know a lot of people kind of go overboard with that, but then don't repeat yourself and all that good stuff in software engineering. But honestly, it doesn't really matter too much. Like, you can hurt yourself by doing it too much for sure, and I think a lot of people do that. Yeah, so this is a very simple example of a common pattern you'll see throughout Haskell, making basic functions that are obviously correct and then combining them into more complex functions. This way you avoid repetition. What if some mathematicians actually figure out that 2 is actually 3 and you have to change your program? You can just redefine double me to be x plus x plus x, and since double s calls double me, it would automatically work in this strange new world where 2 is 3. So yeah, exactly what I just said. I did not read ahead on that, but I feel like that's just a very common example of functions and why you want to use them sometimes. Functions in Haskell don't have to be in any particular order, so it doesn't matter if you define double me first and then double s, or if you do it the other way around. Okay, good to know. So that means that if I wanted to, I could flip this to be the first function. The load would still work, and that would still work. Obviously, from a just reading human standpoint, it kind of makes sense, in my opinion, to have functions defined earlier on that are going to be used later on. But I guess it kind of makes sense that it doesn't matter to the order, because you could probably be including them and things like that later. Now we're going to be to make a function that multiplies a number by 2, but only if that number is smaller than or equal to 100, because numbers bigger than 100 are big enough as is. Okay. We have a function, and we're going to call it double small number here, based off of the book. And it is going to take one number. We're going to refer to it as x. And then it looks like we have a conditional inside of here, so that's kind of cool. So if x is greater than 100, we said we don't want to do anything with it, so I guess we'll just return x or leave x alone. Else we want to x times 2, right? Or I'm just going to go ahead and jump ahead here and use double me again. We might as well use it. The example here has x times 2, but me. So we can reload that. Cool. And let's play around with that. So should double 25, right? Give us 50. Should double 99, give us 198. Should double 100, right? Because it's according to the requirements here, it is it'll double anything that is less than or equal to 100, so we should get 200, but 101 should just give us 101. Excellent. Working as intended. Cool. So right here we introduced Haskell's if statement. You're probably familiar with if statements from other languages. The difference between Haskell's if statement and if statements in imperative languages is that the else part is mandatory. Okay, good to know. So we have to have an else in Haskell. In imperative languages, you can just skip a couple steps if the condition isn't satisfied, but in Haskell, every expression and function must return something. We could have also written the if statement in one line, but I find this way more readable. Another thing about this if statement in Haskell is that it is an expression. An expression is basically a piece of code that returns a value. 5 is an expression because it returns 5. 4 plus 8 is an expression. X plus y is an expression because it returns the sum of x and y. Because the else is mandatory, an if statement will always return something, and that's why it's an expression. If we wanted to add 1 to every number that's produced in our previous function, we could have written its body like this. Let's see here. So it's double small number again with a tick, it looks like, is how they're defining it. X equals, we're doing if, so here it is in one-liner form, the if statement, at least. If x is greater than 100, then x, else, double me 2, or double me x. So that'll return either x or double me x, and then no matter what gets returned, we will add 1 to it. So now if we do this, and we do double, let's do double small number again. So here we did 99, gave us 198, but if we do the new version, it should give us 199. Cool. Same with here, this should give us 201, this should give us 102, so on and so forth. Neat, pretty neat. Okay, so we have had we omitted the parenthesis, it would have added 1 only if x wasn't greater than 100. So had we not done this, this is still valid. Actually, I'm not sure since double me is here. This might even change. So let's load this again. Let's do the double small number, the new one. Let's do 50. So we'd expect this to be 101. Cool. So it does look like it's running the double me before, but what's being said here is if we do 101, it won't actually add it, right? Because this is seen as part, the +1 is in this else statement, right? Rather than adding it after the return of the if expression. Makes sense to me. So that gives us our 102 again, like we expected before. Okay, the apostrophe doesn't have, or note the apostrophe at the end of the function name. The apostrophe doesn't have any special meaning in Haskell syntax. It's a valid character to use in a function name. We usually use the apostrophe to either denote a strict version of a function, one that isn't lazy. Not really sure what that means, but hopefully we'll figure that out later. Or a slightly modified version of a function or a variable, because because apostrophe is a valid character in functions. We can make a function like this. Okay, so it looks like it's just called Conan O'Brien. Yeah, probably would help if I had the right setup here. And it just has, it's me. Conan O'Brien. Cool. If we load this, we should be able to call it, and it gives us the syntax. Cool. So there's two noteworthy things here. The first is that the function name we did capitalize. Okay, the first is that in the function name we didn't capitalize Conan's name. That's because functions can't begin with uppercase letters. Okay, good to know. We'll see why a bit later. The second thing is that this function doesn't take any parameters. Correct, we don't have anything there. When a function doesn't take any parameters, we usually say it's a definition or a name, because we can't change what names and functions mean once we define them. Conan O'Brien and the string it's a me Conan O'Brien, the one that we added, can be used interchangeably. Cool. Alright, so now we are on the section for an intro to lists. Cool. Clear this out so we have a nice blank area to work with. Much like shopping lists in the real world, lists in Haskell are very useful. Cool. I don't know why I keep saying cool, whatever. It's the most used data structure, and it can be used in a multitude of different ways to model and solve a whole bunch of problems. Lists are so awesome. In this section, we'll look at the basics of lists, strings, which are lists, and list comprehensions. And In Haskell, lists are homogeneous data structures. It stores several elements of the same type. So the fact that I said different there is actually completely wrong. Neat. Okay, so that means that we can have a list of integers or a list of characters, but we can't have a list that has a few integers and then a few characters. And now, a list. Note, we can use the let keyword to define a name right in GHCI. Doing let a equals 1 inside GHCI is the equivalent of writing a equals 1 in a script and then loading it. Okay, so it looks like we just have to use let here, so we're going to do let lost numbers equals, and then it looks like a list is denoted with an open square bracket, followed by the items with comma separated, so we got 4, 8, 15, 16, 23, and 42, and then we close it out just like that with a square bracket. And then we can grab that value here, and there it is. Cool. As you can see, lists are denoted by square brackets, and the values in the list are separated by commas. If we tried a list like 1, 2, A, 3, B, C, 4, Haskell will complain that characters, which are, by the way, denoted as a character between single quotes, are not numbers. Speaking of characters, strings are just lists of characters, so the string hello is just syntactic sugar for a list of individual characters, comma separated HELLO. Because strings are lists, we can use list functions on them, which is really handy. A common task is to put two lists together. Actually, I'm just going to write this out real quick. So this is equivalent to this, right, is what they're saying. Oops. Yeah. Cool. Which means we should be able to do this, which is true. Excellent. So a common task is putting two lists together. This is done by using the double plus operator. So if we wanted to do 1, 2, 3, 4, and then add like 8, 9, 10, or create a list of those two together, that should give us, 1, 2, 3, 4, 8, 9, 10. Looks like this works for strings as well, so this would be our string concatenation, it looks like. So here we have just hello world, we're adding a space in between as well, and it looks like we can do this with our individual character lists as well. So we do woo, then we got the oo, t, to give us woot, right? Cool. Watch out when repeatedly using the double plus operator. Is there a better name for that than double plus? I'm sure there is. I should probably like make a little notes tab. I will do that. What is the operator called in Haskell? I am calling it double plus, but there might be a proper name. So there's one. The other one is, what is a lazy function in Haskell versus strict? Or what is Haskell? Or what is a lazy function in Haskell? What is a strict function in Haskell? I'll put those two together because it seems like they kind of mirror each other, so if I answer one, it's probably going to help in answering the other. I'll actually rename those two questions. Cool. Alright, so watch out when repeatedly using the double plus operator on long strings. When you put together two lists, even if you append a singleton list to a list, for instance, 1, 2, 3, plus plus 4, so let me just write that out here. Internally, Haskell has to walk through the entire list on the left side, So in our case, 1, 2, 3. It's not a problem when dealing with lists that aren't too big, but putting something at the end of a list that's 50 million entries long is going to take a while. However, putting something at the beginning of the list using the colon operator, also called the cons operator, is instantaneous. So here's an example of doing that. We have the character A, and we are using the cons operator here, it looks like, to add that to the string small cat. That gives us a small cat. Cool. And it looks like it also works with just a normal list, right? Obviously, where we would add 5 to the beginning of the already existing list, 1, 2, 3, 4, 5, which would give us 5, 1, 2, 3, 4, 5. Notice how cons takes a number and a list of numbers, or a character and a list of characters, whereas double plus takes 2 lists. Okay. Even if you're adding an element to the end of a list with plus plus, you have to surround it with square brackets so it becomes a list. 1, 2, 3 is actually just syntactic sugar for, okay, so we're saying 1, 2, 3 is the same thing as 1, cons 2, cons 3, cons empty list, it looks like. Cool. So we just do 1, 2, 3 empty lists and check that out. That gives us exactly what we were looking for. And let's just say we had a 4 in there already. Cool. That adds that just like that. So that means that the first one is we have this, which would give us 3, which means that the next one, the next application would be essentially that, right? And the last application would essentially be that. Yep. Okay. So it just has a note here where it says like empty list with an empty list, and empty list with multiple empty lists between commas are all different things. The first one is an empty list, the second one is a list that contains an empty list, third one is a list that contains 3 empty lists. Alright, yeah, that makes sense, right? Like, that is not the same as that, which is not the same as that. Yeah. I'm not sure. I'm curious why they noted that here. It seems pretty obvious that those are not the same thing. Okay, cool. So if we want to get an element out of a list by index, use the double bang operator. I guess we have a similar question here. Maybe we just call it like the indexing or something like that. But let's find out what it's actually called at some point. And so yes, if you want to get the element out of a list by index, use double bang. The indices start at 0. So if we want to, I don't know, let's get something out of Conan O'Brien here. Let's get the first letter. This should be I, right? Cool. 2 should be T, or interesting. Oh no, sorry. 2 should be T, obviously, or 1 should be T. 2 is our apostrophe. 3 is our S, 4 is a space. Cool. And it looks like it also obviously works on lists, so if we do this, and we want to get the third element, that should be 4. 0th element should be 1. Neat. Okay, so but if you try to get the 6th element from a list that only has 4 elements, so if we try and do this with like 5, right, because there's not enough, okay, get an exception, prelude, index too large. Lists can also contain lists, but they can also contain lists that contain lists that contain lists. So, okay, yeah, obviously we can just keep making lists of lists of lists, which we kind of knew because we had already seen something like this. So let's do what they're showing here. So let b equals 1, 2, 3, 4. So that's the first list, 5, 3, 3, 3. Second list, 1, 2, 2, 3, 4. Third list inside there, 1, 2, 3 is the last one, so that gives us b. Easy enough. We can use our double operator to add or create So it looks like we do have to do that though, right? Because if we just do this, then I don't think the type is going to be correct. Yeah, because here the difference is we are adding a list of lists that contain numbers, and here we're trying to add a list of numbers which will not be compatible with the type of B. We can do this though, because here we're adding, the cons is that we're adding the entire list of these numbers rather than each individual number. So that one will work, and we can get the index out of here. So if we want to get the second one, looking here, if we wanted to get this value right here, we could do B double bang 2. No, that'll get it for us. Something interesting of note is that while we were working with those B's, it looks like it obviously added the values before, or when we did this version here, it added it at the end because we used the double plus operator, but it doesn't actually modify B. When we still look at B, it's just what we initially defined it here. And I think that's just another property of functional programming, is that it's generally immutable, right? So you can't like change the value of B once it's been defined. I'm sure you can like rebind it using let again. Let's try it, right? Yeah, so it looks like we can do that, but probably I wonder if we can't do that when we're actually in a script, if that's more just a semantic thing with let and trying to make it so this is a little bit more flexible when we're working in the REPL. Alright, so the lists within a list can be of different lengths, but they cannot be of different types. Just like you can't have a list that has some characters and some numbers, you can't have a list that has some lists of characters and some lists of numbers. Makes sense. Lists can be compared if the stuff they contain can be compared. When using less than equals, greater than, and greater than equals to compare lists, they are compared in lexicographical order. First, the heads are compared. If they are equal, then the second elements are compared, etc. And then just some examples here. I'll type them out so y'all can see as well. So we got 3, 2, 1 is greater than 2, 1, 0. And that is true. I'm going to deviate for a second though from the examples just to make sure of my understanding. So when it's saying that the heads are compared if they are equal, then the second elements are compared, etc. So that means that like, I think this could be like 100, and 3, 2, 1 is still going to be greater than 2, 100, 0. Yeah. And that's just because 3 is greater than 2. If we had this, but then it was 3, that's going to be false. If this is the case, though, it'll go back to true. Okay. So back to the previously defined examples. Okay, so yeah, they did something very similar. 3, 2, 1, greater than 2, 10, 100. And that is true because 3 is greater than 2, right? Doesn't matter what the other parts of the list are when it's being compared here. They have 3, 4, 2, greater than 3, 4. Interesting that it will compare lists of different sizes. Cool. And then we can also do like the equivalent here. So we got 3, 4, 2 equals, it is equivalent to 3, 4, 2. That is true. What else can you do with lists? Here's some basic functions that operate on lists. So we have head. Head takes a list and returns its head. The head of the list is basically its first element. So if we call head on 5, 4, 3, 2, 1, that'll give us 5. Cool. Tail takes a list and returns its tail. In other words, it chops off a list's head. Let me just make this, because I'm lazy and I don't want to type that over again. So we have something called list now. So head of list gives us 5. Tail takes a list and returns its tail. In other words, it chops off that list head, so this should give us 4, 3, 2, 1, right? Cool. Last takes a list and returns its last element. Pretty self-explanatory there, so that should give us 1. And init takes a list and returns everything except its last element, so this should be 5, 4, 3, 2. Cool. And then there's a cute little drawing in here, right? So it's like head, tail, init, last. If you were to imagine each of these to be like a segment of a list. Again, this is what I'm following here, Learn You a Haskell. So if you are interested in this, feel free to check it out. It's a free ebook, so that's the reason I feel okay like kind of reading off of it, is that it's content that is freely available to you to check out if you so see fit. Okay, so well, what happens if we try to get the head of an empty list? So let's try that head. Okay, exception, prelude head, empty list, so we get an exception. Oh my, it blows up in our face. If there's no monster, it doesn't have a head. When using head, tail, last, and init, be careful not to use them on empty lists. This error cannot be caught at compile time, so it's always good practice to take precautions against accidentally telling Haskell to give you some element from an empty list. Interesting. Okay, so length takes a list and returns its length, obviously, so if we do this on list, it should give us 5. Cool. Null checks if a list is empty. If it is, it returns true, otherwise it returns false. Use this function instead of list is equivalent to empty list if you have a list called list. So that's essentially just saying make sure that we do, instead of this, we would do this. And null on an empty list should give us true. Cool. Reverses a list. Yep, so now it's 1, 2, 3, 4, 5. Excellent. And takes number and a list. It extracts that many elements from the beginning of the list. So if we do take 3 from our list, it should give us 3 elements. So that should give us the list of 5, 4, 3. If we do take 1 from list, it should give us 5. Cool. And if we do take, 100 from list, so more than we have, it just gives us the list back as it is. And if we take 0 from it, it should just give us an empty list. Cool. See how if we try to take more elements than are in the list, it just returns a list. If we try to take 0 elements, we get an empty list. Drop works in a similar way, only it drops the number of elements from the beginning of the list. So if we do drop 3 instead of take 3 from list, it should give us 2, 1 back, right? Cool. If we drop 0 from the list, it should give us the full list back, 5, 4, 3, 2, and if we drop more than the list, it should give us an empty array. So we had max earlier, which was just between 2 numbers, and min between 2 numbers as well, but it looks like maximum fully spelled out, so if we type out maximum, it takes a list and it returns a smallest, the biggest, and minimum, same thing, but gives us the smallest. Cool. Sum takes a list of numbers and returns their sum, so if we were to sum that list, it gives us 15, and product takes that list of numbers and returns their product. So if we multiply everything together in our list, we get 120. If we sum everything, we get 15. Cool. Obviously, if we have a 0 in there, right? We'll get 0 back because times 0 is 0. Alright, elem takes a thing and a list of things and tells us if that thing is an element of the list. It's usually called as an infix function because it's easier to read that way. So here we're seeing if 4 is an element of the list 3, 4, 5, 6, which it is. And then we can also check, we'll see what happens if it's not, it should get false, cool. And again, this can also be called this way, 4, 3, 4, 5, 6, right? That is the exact same thing as same value from invoking those two functions. So those are a few basic functions that operate on lists. We'll take a look at a lot more list functions later, and it looks like they link off to, what is this, modules. How much later is this? Oh wow, so section 7, so it'll be a little bit before we get there. So the next section is called Texas ranges. What if we want a list of all numbers between 1 and 20? Sure, we could type them all out, but obviously that's not a solution for gentlemen who demand excellence from their programming languages. Instead, we'll use ranges. Ranges are a way of making lists that are arithmetic sequences of elements that can be enumerated. Numbers can be enumerated, 1, 2, 3, 4, etc. Characters can also be enumerated. The alphabet is an enumeration of characters from A to Z. Names can't be enumerated. What comes after John? I don't know. Okay, yeah, that makes sense. To make a list containing all the natural numbers from 1 to 20, you just write open square bracket 1 dot dot 20 close square bracket. Okay. Let me do this. So this gives us the range. Oh, sorry. That would be helpful if I had to. Okay, cool. So now we don't have to type 1, 2, 3, 4, 5, 6 anymore. That's pretty sweet. And there's no difference between writing one or the other, except that writing out long enumerations sequences manually is stupid. I would agree with that. Another example is from A to Z here. Cool, so that gives us all the letters lowercase a through Z. It looks like there is K, uppercase K through Z. Gives us this. I wonder what happens if we mix them. Oh right, sorry, I forgot. Capital A to lowercase z gives us everything, even some extra characters in between. That makes sense. I think that kind of matches with the ASCII table, right? So, kind of just whatever is going on with that. Ranges are cool because you can also apply a specific, or you can also specify a step. What if we want all even numbers between 1 and 20, or every third number between 1 and 20? So the first example looks like is the even numbers between 1 and 20, so we're going to do 2, 4, dot dot 20. Oh, sorry, there shouldn't be a comma here. That gives us 2, 4, 6, 8, 10, cool. And if we wanted to do every third number, I think we'd start with 3, go to 6, and then 20, so 3, 6, 9, 12, 15, 18. Cool. It's simply a matter of separating the first two elements with a comma and then specifying what the upper limit is. While pretty smart, ranges with steps aren't as smart as some people expect them to be. You can't do 1, 2, 4, 8, 16, dot dot 100 and expect to get all the powers of 2. Firstly, because you can only specify one step, and secondly, because some sequences that aren't arithmetic are ambiguous if given only by a few of their first terms. Yep, that makes sense as well. So, it's cool, there's steps, but it has to be for simple steps. To make a list with all numbers from 20 to 1, you can't just do 20 dot dot 1. What happens if we do that, actually? It gives us an empty list, cool. So we have to do the first step here to do it in reverse, it looks like. Cool. And that makes sense because 20, if we're starting at 20 and going to 1, there would be no items there. So it needs to understand that it's going backwards, or down a step rather than up a step. Watch out when using floating point numbers and ranges because they are not completely precise by definition. Their use in ranges can yield some pretty funky results. 0.1, 0.3, dot 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 1, or dot dot 1. That is weird. So the advice in the book is to not use them in list ranges. Easy enough. You can also use ranges to make infinite lists just by not specifying an upper limit. Later we'll go into more detail on infinite lists. For now, let's examine how you would get the first 24 multiples of 13. Sure, you could do 13, 6, dot, dot, 24 times 13, but there's a better way. So he's saying that this is a way you could do it. Dot, dot, 24 times 13, that would give us that. But we can also do take 24, 13, 26, dot, dot. So again, we're using our list function. We're saying we want the first 24 elements of this list that we're creating, 12, 26, dot, dot. That gives us, actually gives us something different. Oh, sorry, because I need to start with 13, not 12. There we go. So we got 13, 26, 39, 52, 65, 78, which is the equivalent of that 13, 26, 24 times 13, right? Cool. Those are the same. Alright, because Haskell is lazy, okay, so there's that concept of lazy, and it won't try to evaluate the infinite list immediately, because it would never finish. Yep, that makes sense. It'll wait to see what you want to get out of that infinite list. And here it sees you just want the first 24 elements, and it gladly obliges. A handful of functions that produce infinite lists. Cycle takes a list in a cycle and cycles it into an infinite list. If you try to display the result, it will go on forever, so you have to slice it off somewhere. Alright, so we can do a take here as well. The example has take 10 of the cycle of 1, 2, 3. And that gives us 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. We can also cycle, it looks like, on strings. So if we do take 12 of cycle LOL with a space, gives us LOL, 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 LOL. Fun. Repeat takes an element and produces an infinite list of just that element. It's like cycling a list with only one element. So if we do take 10, repeat 5, gives us 10 5s. Cool. Although it's simpler to just use the replicate function if you want some numbers of the same element in the list. Okay, so if we wanted the same, we can also just do replicate 10 5. That should, or if I spelled replicate right. So those is equivalent to take 10, repeat 5. Cool. A list comprehension. So if you've ever taken a course in mathematics, you've probably run into set comprehensions. They're normally used for building more specific sets out of general sets. A basic comprehension for a set that contains the first 10 even natural numbers is, and I'll just pull this up here as mathematical notation, the set equals 2 times x, where x is a natural number and x is less than or equal to 10. The part before the pipe is called the output function. X is the variable, n is the input set, and n being the natural numbers is the input set, and x less than or equal to 10 is the predicate. That means that the set contains the doubles of all natural numbers that satisfy the predicate. If we want to write that in Haskell, we could do something like take 10, 2, 4, dot, dot. But what if we didn't want doubles of the first 10 natural numbers, but some kind of more complex function applied on them? We could use a list comprehension for that. So list comprehensions are very similar to set comprehensions. We'll stick to getting the first 10 even numbers for now. The list comprehension we could use is x times 2, pipe x is the list 1 through 10. X is drawn from 1 through 10, and for every element in 1 through 10, which we have bound x, we get that element only doubled. Here's the comprehension in action. So let's write that out real quick. Let's play with that. So we got x times 2 pipe x is the list of 1 through 10, and that gives us that. Since we are in our thing, we could also do, it looks like, I believe, double me, right? double me x gives us the same thing, again using a function we defined earlier that does the functionality we want. As you can see, we get the desired result. Now let's add a condition or predicate to that comprehension. Predicates go after the binding parts, so the binding being this, right? That was the binding there. And are separated from them by a comma. Let's say we only want elements which, when doubled, are greater than or equal to 12. So we could do this, and then it's x is greater than equal to 12. Oh, interesting. There we go. So it actually is that we want to check that the doubled value of x is greater than 12, and then that is what actually gets added. Okay. Cool, it works. How about if we wanted all numbers from 50 to 100, whose remainder when divided with the number 7 is 3? Okay, let's work that one out. So we want some number from 50 to 100, so we're going to do x, and then x is going to be bound to the list between 50 and 100, where when divided that number by 7, we get the value 3. So I think we'd want to use the modulus, right, or mod. We can infix it, so we'll do x mod 7 is equivalent to 3, right? I think that works. Yep. Cool. And that's just because we were looking for the remainder, so that's why the mod, I think we can do like lim as well. Yeah. I don't know which one's better, to be honest. In the example they have mod for modulus, which makes sense. I mean that's something that's known for most programming languages. Usually it's the percent sign. Maybe I'll look that up. Another question to ask. And maybe these questions I can kind of like dive into them and try and tackle them at the beginning of the next stream before jumping into learning some more. That'd be cool. Alright, so success. Note that weeding out lists by predicate is also called filtering. So essentially we're just saying we're filtering that list based off of the values that are give us a remainder of 3. Now for another example, let's say we want a comprehension that replaces each odd number greater than 10 with bang, and each odd number that's less than 10 with boom. If a number isn't odd, we throw it out of our list. For convenience, we'll put that comprehension inside a function so we can easily reuse it. So we'll use that function up here, and they're calling it boom bangs, and it takes a list xs. So here's our list comprehension. So we're saying if x is less than 10, then boom, else bang, right? So that's our evaluation that's happening, or our expression. And then we are doing x is our list, and we are filtering it using this function odd. So let's do odd 1, odd 2, cool. So it looks like odd is just a function that takes a number, I'm assuming, right, because if I do like odd foo, it should tell me, yeah, it's looking for an integral. I'm assuming this doesn't work as well. Holy shit, that blew up. Cool, alright. So here's our function here. It will, I guess, I like reading it from here first, to be honest. So we bind our that we're passing in our list to X. We filter out. Actually, what? Okay, that doesn't work either. So then, per each of those, we or for each X, we filter out if it's odd or not. And then after we do that, if it's odd and it's less than 10, we have boom, else it's bang. So if we were to do, let's load up our thingy here, and then if we did boom, bangs for the list of, in this example, 7 through 13, it gives us boom, boom, bang, bang. Neato. We can include several predicates. If we wanted all the numbers from 10 to 20 that are not 13, 15, or 19, we could do the following. So we're going to do x. X is bound to 10 through 20, and we're doing x is not equal to 13. And it looks like they want to do that. We want to do that for both 15 and 19 as well. X is not equal to 15. X is not equal to 19. That's our list: 10, 11, 12, 14, 16, 17, 18, 20. Cool. I'm sure if we were to actually write that, we'd probably have like a list with those numbers we didn't want it and have it be like not, right? Like I think that would be the other way. Or like not in. Actually, I'm gonna rewrite that. I'm gonna try that. So if we wanted to make this slightly more condensed, because we don't like doing the x not equal to 13, x not equal to 15. What if we did not x lm 13, 15, 19? Will that work? Will it work if we do it like this? Cool. Obviously they were in the book showing it that way to show multiple predicates, but I was just curious to see how we could rewrite this using our current knowledge. So we knew about the not, we knew about the lm, and we can write this and get the same result in a more compact way, because now we can have that list be a lot more flexible. Cool. Alright, so not only can we have multiple predicates in list comprehensions, an element must satisfy all the predicates to be included in the resulting list, we can also draw from several lists. When drawing from several list comprehensions, produce all combinations of the given lists, and then join them by the output function we supply. Alright, a list produced by a comprehension that draws from two lists of length 4 will have a length of 16, provided we don't filter them. So if we have two lists, 2, 5, 10, and 8, 10, 11, and we want to get the products of all possible combinations between numbers in those lists, here's what we do. So we'll get the combination of the products, and x was what? It was 2, 5, 10, right? And then y is going to be 8, 10, 11. That gives us this: 16, 20, 22, 40, 50, 55, 80, 100, 110. Cool. As expected, the length of the new list is 9. What if we wanted all possible products that are more than 50? So we do the same thing that we're doing right here, and then we would just do x times y is greater than 50, right? And that gives us 55, 80, 100, 110. Sweet. How about a list comprehension that combines a list of adjectives and a list of nouns for epic hilarity? Alright, let's try it. So here we have our nouns. Is hobo, frog, pope. And then our adjectives are lazy, grouchy, and scheming. cool. So our list comprehension, we're going to take an adjective and append that to an empty or a space with a noun. Then we're going to do adjective, and the noun is bound to nouns. Boom. So that gives us all of them. So we have a lazy hobo, lazy frog, lazy pope, grouchy hobo, grouchy frog, grouchy pope, scheming hobo, scheming frog, scheming pope. Good. Alright, so we can write our own version of length as well, and since we are just kind of renaming it, we can use that apostrophe like we did earlier. So we're going to take length of XS, and it is going to be the sum of this list comprehension here. So we have length of list, which give us, oh wait, so when it reloads it looks like we lose everything there, that's fine. Let's do let list 10. So now here we have lists, so now we do length of list, that gives us 10, and our length of list should also give us 10, cool. So the underscore here, the book is saying, means that we don't care what we'll draw from the list anyway. So instead of writing a variable name that we'll never use, we just write underscore. The function replaces every element of a list with 1 and then sums that up. That means that the resulting sum of the list will be the resulting sum will be the length of our list. Okay, yeah, that makes sense. Just a friendly reminder, because strings are lists, we can use list comprehensions to produce, process and produce strings. Here's a function that takes a string and removes everything except uppercase letters from it. So we're calling it remove non-uppercase. It's going to take a list, or they're going to call it st, and then we're going to do a list comprehension where it's c, and then c, we're going to bind that to the input value. So we want it to be an element of a through Z here. You figure out. So this is definitely like an extension that I have that's adding these in, but I don't like that it like freaks out and moves all over the place. So maybe I should disable that at some point. A little annoying to look at. Cool. So let's load that. We're gonna do remove non-uppercase of ha 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 ha. That should give us ha. And then I don't like frogs. Gives us I like frogs. Cool. Easy peasy. So it says the predicate here does all the work. It says that the character will be included in the new list only if it's an element of the list A through Z, obviously capital A through capital Z. Nested list comprehensions are also possible if you're operating on a list that contains lists. A list contains several lists of numbers. Let's remove all odd numbers without flattening the list. So here we have a list of lists. 1, 3, 5, 2, 3, 1, 2, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 4, 2, 1, 6, 3, 1, 3, 2, 3, 6. So there's our list of lists. And then here we're going to return a list. so we're having a list comprehension inside of a list comprehension of all the even numbers, and XS is going to be bound with XSS, right? Sorry, XXS. There we go. Cool. 2468, 242, 626. I had an extra 4 inside that XS list. This should have been 5. If we rewrote that, now we have the same output as in the book. Cool. You can write list comprehensions across several lines, so if you're not in GHCI, it's better to split long list comprehensions across multiple lines, especially if they're nested. Cool. So these things are the type signature though, I think. And I know that if I click it, it will just add it, which is cool, but again, I want to not get ahead of myself, and I will start writing those. So hopefully that'll stop actually the jostling once I get to that point. Hey, what's up, Vivax? How are you doing? Alright, so tuples. In some way, tuples are like lists. They are a way to store several values into a single value. However, there are a few fundamental differences. A list of numbers is a list of numbers, that's its type, and it doesn't matter if it has only one number in it or an infinite amount of numbers. Tuples, however, are used when you know exactly how many values you want to combine, and its type depends on how many components it has and the type of component. They are denoted with parentheses, and their components are separated by commas. Hey, that's good to hear. Liking it so far. It's very early in the stage, or very early in my learning, obviously. I'm using this resource currently that I'm sure everyone who's ever learned Haskell knows about, the Learn You a Haskell. Just kind of going through that first section right now to get a feel for it, if you will. Are you a Haskeller yourself? Alright, so another key difference of tuples is they don't have to be homogeneous. Unlike a list, a tuple can contain a combination of several types. Sweet. Oh, nice. What part are you in so far? Alright, so think about how we'd represent a two-dimensional vector in Haskell. One way would be to use a list. That would kind of work, so what if we wanted to put a couple of vectors in a list to represent points of a shape on a two-dimensional plane? We could do something like a list of lists, obviously, where we have 1, 2, 8, 11, 4, 5. Cool, so that would give us that. Oh dang, 13. So you're basically a Haskell expert at this point, right? Let's see if I can check this out real quick. So do you come from another programming language background, or is this like your first language that you've learned Haskell? I work as a software developer, so I work in a lot more imperative languages, worked in like C, Java, JavaScript, all that fun stuff. So I'm at the point right now where it's like, alright, a lot of these words I'm understanding, right, obviously, because they have a similar context, but at the same time, there's some extra stuff to wrap my head around. Oh nice, Python. Yeah, I've unfortunately haven't had a lot of things to do with Python since graduating a while back, so I haven't really used it since I think I was like a freshman or sophomore in college. I feel like it's changed a ton though.
Thank y'all for being aides, some of you, constantly. Coco, I don't know, I'm not really good at impromptu speeches. Just adding me.
Alright, so doing this but as tuples, we could have a list of tuples. Cool. So what's been like the weirdest shift for you in learning Haskell so far? I've kind of peeked ahead, so I've heard of the scary monad and things like that. I think I have some idea of like what a functor is, just from working through some other projects in other languages, but I want to make sure that once I get to those, I like have a firm understanding and not just I make this sequence of text in a text editor and it works and I don't know why. So let's make this error here. So since tuples have a type signature for amount and type, this should give me an error for not having a homogeneous list. Cool. Couldn't match expected type AB with actual type integer. Oh yeah. Yeah, I could definitely see that. Do you like if you had to choose right now, which style do you kind of prefer? The like thinking in classes kind of structure, or the more like data-based flowing through function to function style of reasoning about your programs? Because I think that's kind of like what draws me to functional programming, is I really like the idea that it's kind of almost like a pipeline, right? Where you take some data, you pass it through, everything's kind of understood with its parts, and then you get some data out at the end. I've always kind of liked that outside of the wrapping things in classes and working with objects and stuff like that. Like ultimately you can get things done with both of them, but it just kind of seems cleaner, obviously, in the functional way. If not more overhead to get everything set up, but just, I don't know. It's what appeals to me, I think, is just that pipeline of data. Alright, so it says I should use tuples when I know in advance how many components some type of data should have. Tuples are much more rigid because each different size of tuple is its own type, so you can't write a general function to append an element to a tuple. You have to write a function for appending to a pair, one for appending to a tuple, for a triple, one function for appending to a four-tuple, etc., etc. While there are singleton lists, there's no such thing as a singleton tuple. It doesn't really make much sense when you think about it. A singleton tuple would just be the value that it contains, and as such would have no benefit to us. Oh, true. Yeah, I guess when you want to work with something with a little bit more statefulness, it's easier to get it up and running in things like Python. That does make a lot of sense. Do you work with software professionally, or is it more of a hobby, personal project type thing? Yeah, so yeah, it said no singleton tuple. Yeah, so I think what they were saying there is not the unit per se, but like this. Like, yeah, that exists technically, but because it's just the value inside of here, that there's no reason to use it rather than just using. Yeah. No, it is weird. Singleton and unit. Yeah, no, I think I've heard of unit, which makes sense.
Better understand and control our own planet.
No, terminology, especially with learning a language like this, is super important. So it's definitely it's good to point that out, because now I have drawn attention to singleton versus unit in my mind, which I may not have already. Like I have a questions document I'm coming up with, essentially, where I'm like, okay, double plus operator, I'm calling it that, but I'm sure there's a proper name. Like, I don't know if it's like concat essentially, right? But maybe it's not called that, or like the double bang, and like what's the difference between lazy and strict. So I'm creating all that, creating a document so that way I can go back and answer all those questions for myself, because otherwise I feel like it's going to be a pain to learn all this. Alright, so two useful functions that operate on pairs. We have the FST function, or first, I'm assuming, which will give us the first value here. Cool. And then second, which would give us obviously the second value in a pair. Neat. Just gonna mix these up so that way I can kind of get that in my head that I can do that. So obviously those functions only operate on pairs. They won't work on triples, four tuples, anything like that. We'll go over extracting data from tuples in different ways a bit later. Cool. So if you're on section 13 at this point, how long have you been learning, if you don't mind me asking? Because this definitely seems like something like I could kind of breeze through, maybe do a section a day or something like that, but I'm worried that if I do it that fast that I'm going to be forgetting a lot of stuff, so I'll probably do a lot of backtracking and a little bit of side stuff. Maybe try and hack on some like advent of code stuff with my current Haskell knowledge, see if I can exercise it a little bit, things like that. Alright, a cool function that produces a list of pairs is zip. It takes two lists and then zips them together into one list by joining the matching elements into pairs. It's a really simple function, but has loads of uses. It's especially useful for when you want to combine two lists in a way or traverse two lists simultaneously. So a demonstration of those, it looks like they're just zipping two lists here. And then, cool. That gives us a list of the tuples. And then the other one that they give is that zip 1 through 5 again, but with the words. Oh, nice. Well, yeah, so I do plan on streaming. I don't know if I'll do it every day or every other day, but just generally in the mornings. So hopefully if you're curious and you want to hang around and drop in every once in a while, you can correct me on things that I'm doing incorrect as the as the person who's traversed ahead of me. Oh, nice. Let's see, what's section 12? Oh, yeah, just to kind of get more and more into the monads. The only thing I've seen about monads is people using burritos or something to trying to describe them, and then another, like half the people are using that, and the other half are trying to say that describing monads as burritos is a really stupid way to describe it. Like my very, very, very naive understanding of it is it's just a construct to contain side effects, right? Like it's a mathematical structure to contain side effects. That is all I can tell you, and that could definitely be wrong. Alright, so it pairs up the elements and produces a new list. The first element goes with first, second with second. Cool. Notice that because pairs can have different types in them, zip can take two lists that contain different types and zip them up. What happens if the lengths of the list don't match? So if I were to do, I don't know, zip 1 through 20, and in this case they said, I'm a turtle. Interesting, so it will just take the smaller of the two lists and only zip until the end of that. Well, the idea idea the book gives is that is a value with a context, a list is a context, that there might be 0 more value I as a context, that we will get the value from the outside world maybe as a context. Gotcha. Yeah, it'll be fun whenever I get there, because that seems like the first big hurdle to be able to call myself a Haskell programmer, is to be able to effectively work with monads. See, like, things like maybe, I get as, like, an idea in programming, if that makes sense. Another language that I like to mess around with and that I want to get into again at some point is Rust. The same problems I have with Rust and Haskell is that I just don't know what to do with them once I learn them. Like, I enjoy learning them as in learning a new language, but I don't really know what projects to do to actually, like, exercise and make use of that. So that's also another reason kind of why I wanted to stream, is because I figured it'd be fun to jump in with the community of people who are more creative than I am in terms of projects, so that way it would be more of a collaborative effort, so that way when I'm learning the language I can actually do interesting things with it afterwards. But anyways, that was kind of a side tangent there with maybe, but like there's that concept in Rust where you can have it wrapped so that way whatever is making use of the value has to handle all the possibilities of it existing or not existing, which is kind of cool. But again, from my standpoint, not a huge, I haven't made that connection of what that means and why that's a monad in Haskell. Oh, nice. Yeah, I've seen Exorcism before. Would you recommend it? Is it a good kind of a way to flex and learn? See, in the Twitch bot, yeah, I feel like that seems to be like the hello world of Twitch streaming, so I'm sure I'll make that as well. And it also is like an interesting project because you actually have to do like network calls and things like that, so I feel like that would be a really good one to do, especially with Haskell. I'll probably also make a list of that, of project ideas at some point. Alright, so the longer list simply gets cut off to match the length of the short one. Because Haskell is lazy, we can zip finite lists with infinite lists. Yep, that makes sense, given what I know so far. So we can just take an infinite list here, and then yep, cool. And that makes sense because, I mean, it's the exact same functionality as what happened earlier when I just had a longer list. So when you say you have like feedback on your code, is it that other people you're able to like have other people look at what you post on that exorcism, or is it kind of like a bot evaluates the code that you wrote and gives suggestions and things like that? I haven't actually used that site in like 2 or 3 years at this point, now that I think about it. Yeah, and you're saying like, you know, you might write code and then someone else can tell you like, yeah, you wrote this huge function over here and you can do that with using this built-in function. You're like, oh yeah, sweet, now I know. So here's a problem that combines tuples and list comprehensions. Which right triangle that has integers for all sides and all sides equal to or smaller than 10 has a perimeter of 24? First, let's try generating all triangles with sides equal to or smaller than 10. So we're going to create our triangles here. Our list comprehension is going to return list of tuples. We're going to have 3 tuples. We're going to call them A, B, and C. C is going to be bound to the list of 1 through 10. same exact thing. Let's see what triangles looks like now. That is a lot of triangles. Sweet. Man, I got a new keyboard and it's so much like more sensitive than I'm used to, so I keep like mistyping all the time just by brushing my finger. Okay, so you can publish your solution and they can leave comments, but you can also request a review from a mentor. And the core exercise requires a mentor to review it before you can move on, though you can switch to a mode where you don't get comments. Oh, that's cool. Yeah, no, I definitely should look into that then, if there's mentors and everything. That sounds incredibly useful. Also, thanks for the follow. Like I said, I'm a noob streamer, so I didn't see that before, but I appreciate that. Oh, nice. Yeah, I think I'll actually just open up a tab here so that way I don't procrastinate. Did you wait a little while before using it? Like, did you get a little bit further in the book, I'm assuming, just to have a little bit more? Ooh, and there's so many languages on here now. It's funny because like as much as I want to use Haskell long term too, and I want to try and do as much with it as I can, like I know that I'm gonna find myself leaning towards things like Reason ML, so that way I can try and use a little bit more functional programming in like web development and stuff like that. But so I see that's on here. That's pretty cool. Alright, so here is our huge list of triangles. So now if we want to find the right triangles, we can use another list comprehension. Which will also give us a tuple. But this time, we're going to do okay, so I see why they wrote it as CBA now, because we bind C to the list of 1 through 10, B will be bound to the list of 1 through C, and then A will be the list bound 1 through B. And then our filter is going to be A squared plus B squared equals C squared, right? A squared B squared equivalent to C squared. That should give us our right triangles. Okay, so that's 2 of them. So we're almost done. Now we just need to modify the function by saying that we want the ones where the perimeter is 24. So we can just create a slightly different one here. And then we add one more predicate where A plus B plus C is 24. That gives us 6, 8, 10. Sweet. So you start using after 12, but the first ones you can do before 12. You can always just go back to the book if it gets hard. Yeah. Like you don't need to know about monads to make a function to return if it's a leap year. Not true. Yeah. Yeah, it seems like monads are like first introduced as like IO, right? That's kind of like the impression I get, is that's going to be the first ones that will be more useful as getting user input and actually outputting the result of stuff to the program. Gotcha. Yeah, maybe makes sense as well because it seems pretty straightforward. Like at least the functionality behind it seems to be pretty straightforward. Let's see. I'm gonna look ahead. I'm gonna cheat. Okay, so yeah, input output starts at 9, but I don't know how much they jump into monads, and then yeah, fistful monads. It looks like it starts with maybe. Sweet. Alright, so since I just finished up that first section, so it looks like next I'll be looking at types and type classes. I'll probably save that for next time. Coming up on 2-ish hours of streaming here. Gonna hop off, take care of some stuff. Yeah, hey, thanks for hanging out with me for a bit here. I hope to see you around sometime soon. Hopefully I'll have a little bit more knowledge under my belt next time. And thanks for the tips on exorcism. I will definitely check that out. Yeah, catch you later.